Hi, my name is Vikas and I am from the Mechanical Engineering Department. And the title of my talk is Control-Oriented Modeling of Complex Hydronic Systems. This work was done in collaboration with an undergraduate student, Gina, in our lab, and my advisor, Professor Aline. So here is a brief outline of my talk. So in the first few slides, I will introduce hydronic systems from a physical and modeling perspective. And then I'll go on to explain the details about the particular modeling approach that we have used. Excuse me. That will consist of a full order model, model reduction, model evaluation, and then I will wrap up with some concluding remarks. So hydronic systems are thermal management systems which use water for the transport of energy. And the most common applications of these systems are for the heating and cooling of buildings, which includes residential buildings, commercial buildings, data centers, etc. On a much larger scale, the application is for cooling or heating of entire districts. And here on the left is the schematic of a typical district cooling system, where chilled water is being supplied to all the various buildings in this system so as to meet their individual cooling requirements. On a much smaller scale, there are some applications like, for example, in the thermal management of automotives or for cooling of electronic circuitry. And in this work, our focus is on hydronic systems that are used for building heating and cooling. Now, talking about buildings, there are certain statistics which motivate this work. In the US, buildings account for around 40% of total energy consumption. And furthermore, they are responsible for around 1/3 of total greenhouse gas emissions. And if you look at a typical building, now this is end-use energy consumption for a residential building. We see that space heating and cooling together account for around 35%, 35 to 40% of total energy consumption. So this shows that there is an opportunity if we make these heating and cooling systems more efficient, that we can create a significant impact on the energy and emission scenario overall. Now here, I would like to explain one of the main characteristics of these systems, and that is complexity. We are focusing on large-scale systems, and these large-scale heating or cooling systems can be very complex. They consist of a number of components, and the components are intertwined together in a complex fashion. This is the schematic of a cooling system for a high-rise building in Hong Kong. So here is a list of the requirements from a modeling point of view. The model that we would like to present should be representative of all the dynamical interactions between the various components. And in the previous slide, I showed how complex these systems can be. So we would like the model to be simple enough so that we can do control design work easily on that. Apart from that, we would also like the model to be generic, meaning that it should be representative of a wide variety of these systems, whether it be heating systems, cooling systems, or large scale, small scale. So it should be pretty widespread. And then the last thing we would like the model to have is flexibility, meaning that if there are some physical changes done to the actual system, like you add a component or remove a component or change the operating conditions, it should be easy to update the model correspondingly. So here is a look at how in the past people have looked at modeling of these systems. And on the columns here are the various requirements, modeling requirements. And we see that there's no work which addresses all these issues at the same time. And we would like to fill this gap and present a model which achieves all these various objectives. So now I come to the presentation of the modeling framework that we have used. And this flowchart summarizes our approach. But before that, I would like to explain a little bit more about these systems from a physical point of view. So if we talk about these systems, the components can be categorized as either thermal components or hydraulic components. The hydraulic components are typically the pumps, the valves, the flow junctions, and they are associated with the circulation of flow in the system in the various sections, and also the control of that flow, depending on the loads, the heating or cooling loads that are required in that section in a particular room, for example. The thermal components can be categorized as source components or sink components. The source components are typically boilers in a heating system or chillers in a cooling system. The sink components are the heat exchangers, which serve the conditioned air to the various spaces in the room. So the first step in the modeling is the modeling of connectivity, which tries to capture the complexity in the system. And for that, we use a graph theory approach. And the reason for using graph theory here is that it has been used in the past for a lot of similar complex systems in the area of communication networks, power systems, process networks, and also some other applications. And to explain the particular graph-based approach that we have used here, I used the same example that I showed earlier. This is a small-scale heating system, and here is the corresponding graph for it. The graph, the first thing to note about the graph is that it's a directed graph, and the edges are directed according to the direction of fluid flow in the actual physical system. The vertices of this graph are of two types. We have mass flow vertices and energy flow vertices. The mass flow vertices, which are shown by these hollow circles, they correspond to the flow junctions, where the flows meet or split in the actual physical system. The energy flow vertices are representative of the thermal components, and they are shown by these solid circles. So they correspond to the boiler and the heat exchangers here. And then, apart from these vertices and edges, we also defined some special elements in the graph, and they are called pipes. And I'll explain it here with this example. So pipes are defined as directed edges between any two mass flow vertices. So for example, if you pick mass flow vertex number 2 and mass flow vertex number 3, then this path, which goes from here to here and which consists of edge number 2 and 3, is a pipe. So similarly, you can find all the pipes in the system. So once we have obtained the graph representation, the next step is to capture the connectivity information from the graph, and that is extracted in the form of certain matrices. So as an example, I show one particular matrix here. I call it the pipe junction incidence matrix. The columns here are the pipes, the rows are the junctions. And let's look at this one, this particular pipe which I showed in the last slide. This is pipe number 2. I just number it like that. And it leaves junction 2 and enters junction 3. So we put a -1 in this position for junction 2 and +1 in this position for junction 3, and then zeros everywhere else. And in a similar way, we construct this entire matrix. And in a similar fashion, we also obtain 5 other connectivity matrices. So altogether, we have 6 matrices from the graph, which capture the connectivity information in the system. After capturing the connectivity information, the next step is the modeling of the individual components and all those components that I showed earlier, the hydraulic components, the thermal components. So we want to obtain linear, simple models for these systems, for these components. And for that, we need to prescribe certain operating conditions about which we would derive the model. And there are certain variables associated with each of these components. So we would like to obtain the operating values of those variables. And a typical way of doing that could be using a combination of measurements or using some kind of a nonlinear physical equation, governing equation for these systems, for these components, or maybe using some kind of simulation or system ID. So once we obtain the operating conditions for each of those components, the next step is to obtain the linear models about those operating conditions. And for that, we can use either we can conduct some experiments close to the operating point, or we can use analytical derivation based from the first principles, or maybe use some kind of simulation. So these are the general structures of the various governing equations, the models. So first of all, we have pipes. And pipes refer to those special elements of the graph that I showed before. And the governing equation here is the conservation of momentum. As you see, it's a first order linear differential equation, which is what we want. We are deriving linear models. The next component is the mass flow vertices, which correspond to the junctions. And there we have the conservation of mass and conservation of energy. Then lastly, we have the energy flow vertices, which correspond to the thermal components. And there we have energy conservation applied to the fluid inside it and the structure surrounding the fluid. And this is an algebraic equation which relates the output, the desired output, to the states. And the desired output is the amount of heat transfer that you obtain from these components, from the sink components to the various zones in the building. So what we do is then all these various coefficients, we assemble them together into some matrices and call them coefficient matrices. Then we connect the connectivity and the coefficient matrices to obtain the state space model. And this is what the final form looks like. So this is the state vector, and it consists of 5 different sets of states. So each of these is actually a vector. So it's a long big vector. The states are the various mass flow rates and pressures in the hydraulic components, and the temperatures in the thermal components. And we also, the inputs here, some of these inputs can be treated as control inputs, like we have valve opening factors or pump speeds, assuming variable speed pumps. Some of these are like disturbances. For example, the inlet air temperature, which normally is the ambient temperature, or a mix of the ambient and the air that is recirculated, or also the air mass flow rates. This is the other part of the model. So this relates the outputs, and as I said, the outputs are the final heat transfer that we achieve in the sink elements to the states and the inputs. So as I mentioned, that complexity is a big issue when it comes to these systems, and the model that I just presented, the full order model, it does not do anything to eliminate that complexity. So we would like to go a further step and try to obtain a simplified version of that model, which would aid the process of control design. And the motivation for doing that is this time scale analysis of the dynamics in the system. And on the x-axis here, I show the various states, the various sets of states. So these are the hydraulic states, these are the thermal states, and these are the typical time constants. And this graph was calculated, was obtained for a specific example. And here are some typical values that we see. So we can see that some of these states are much more dominant when it comes to the dynamics. The dynamics is much more slower than the other states, and it's a lot of difference actually if you see compare this and this. So this is the motivation for doing the model reduction. And what we do is we treat the faster states, these states, as static. And once we do that, it's a bunch of algebra, and then finally we come up with the reduced order version where the states are only the ones that matter, which are the ones with the slowest dynamics. In this case, they are the wall temperatures in the heat exchangers. So once we obtain the reduced order model, the next step is to validate it. For validation, we use a system which is slightly more complex than the heating system I showed before. This system has 2 chillers. It has 6 heat exchangers, and then correspondingly 6 control valves for each of these. And these heat exchangers serve a zone or a cluster of zone. So typically, I would say it represents a building with 2 stories, one set of these for each of these stories. And we have a nonlinear model of this system, and this is mentioned in this paper. And we validate our linear modeling, the reduced order linear modeling approach against that nonlinear model, and these are the results. So this is test case 1, where we perturb the inlet air temperature in the heat exchanger, and we see that there is very good correlation both at the steady state and the transients. This is the test case 2, where we perturb the valves 1, 2, and 3 that correspond to the first 3 heat exchangers. Again, the observations are similar. Test case 3, we perturb the operating capacity of the first chiller out of the 2 chillers, and there's some small amount of steady state error, but that's still within 10%, so it should be good for control design purposes. So this is the presentation of the model, and the next step that we would like to take is control design based on that. And actually, we have already designed some controllers based on the model, and we see some significant improvements over the baseline when it comes to the performance of those controllers. So to wrap up this presentation, I presented a generic modeling framework and applied the model reduction to the presented model, and we saw it offer significant complexity reduction. I should mention that in this the test case example that I showed, the number of states here went down from 55 to 8, which is a significant reduction. And reduced order model showed satisfactory behavior. In the future, we would like to do control design, as I mentioned, and also include some other components like zones. Also, these days, most of these systems use thermal storage to change the peak, change the load distribution. So that is what we would like to include, and also like to add combined heat and power capability, modeling capability in these models. So yeah. So if you have any questions, I would like to answer that. So typically, the control for these kind of systems is very heuristic. It's mostly on and off control, which right now, yes, that's the state of the art right now, and it doesn't use any kind of model. And what we have done is we have used these models to develop model predictive controllers, and we see some percentage improvement. I cannot cite that because it's not published yet, but yeah. Yes?
There's a trade-off between the comfort in the buildings and how much energy is
Sure.
into them, and how do you take that into account?
So the control approach that we use, that's a question that that's more relevant to the control part. We capture all this in an objective function, and then change the weights. There's a term for the comfort. There's a term for the energy. There's a term for robustness. So all these various things that you would like to achieve, you can model that in a cost function, and then design your controllers based on that. But we need a model for that. That's the important thing, and we need a simple enough model, and that's the first step that I presented in this work for that.